Vibrational mode analysis is a powerful tool for identifying vibrationally active modes and assigning spectra. Hi, I'm Riley, Chemist Rogan, and today I'll be taking you through this incredibly fascinating topic. Let's start out with water. Water has 3 atoms, 9 total degrees of freedom, and 3 vibrational degrees of freedom. But how can we match them up to each reducible representation? The point group of water is C2V, and we must find a reducible representation for all motions of water. A nice trick for this is to sum each irreducible representation that corresponds to X, Y, and Z translations, and then multiply those values by the number of unmoved atoms that result from each symmetry operation. Using this method, we find that the reducible representation for all motions is 9, -1, 3, and 1 for the 4 classes. Combining this information with the character table, we can use the following equation to decompose our reducible representation to discover how many irreducible representations of each type there are. We find 9 different modes: 3A1, 1A2, 3B1, and 2B2. Now we can eliminate the translational and rotational modes by using the basis functions to tell us which correspond to translations and rotations. This just leaves the following vibrational modes. But what do they look like? Let's head down to the lab to find out. Using cutting-edge motion capture technology, we're able to simulate all 3 vibrational modes for an H2O molecule. The modes are as follows. First, the symmetric stretch. As you can see, the hydrogens are elongating while the oxygen is going up and down. Next, the symmetric bend, which looks like a flightless bird attempting to take off while lowering its head in frustration. And finally, the asymmetric stretch, which is really testing the coordination of our motion capture model. But which of these modes are IR or Raman active? Let's ask our experts and find out.
Riley, you know Brandy's gonna know I've never done this before, right? Like I was in left office, okay, we'll do it. Infrared active vibrations occur only when the dipole moment is changed. When consulting a character table, we can use the basis functions column to see if the molecule transforms as X, Y, or Z to determine whether a mode is IR active or not. The presence and location of IR peaks can help distinguish isomers, but even without the actual spectra, the basis functions can reveal this information as long as there are a different number of active vibrations for each molecule. Whew.
Happy month of December, everyone. I would like to thank my good friend Riley for having me on today. Let's discuss vibrational modes we can see with Raman spectroscopy. Raman active vibrations are produced by a change in polarizability of a molecule. Polarizability refers to the ability of a molecule's electron cloud to be distorted by an induced electric field. This variety of vibrations can be identified for each irreducible representation that corresponds to the quadratic basis functions. Because Raman spectroscopy detects different properties than IR, it adds another dimension of selectivity to our vibrational mode analysis. This is important because even if isomers have the same number of IR active modes, you could use Raman to distinguish between the two. Raman measurements are useful for analyzing many molecules and also for important materials like indium phosphide.
Relating this information back to our water example, all 3 vibrational modes would be both IR and Raman active because each irreducible representation corresponds to both linear and quadratic basis functions. We would only see a different number of peaks in IR and Raman spectra if a mode has a translational mode in the first basis function column, but not in the quadratic column, or vice versa. Thanks for joining me on this wild adventure through transition metal chemistry. I hope you learned more about the topic, vibrational mode analysis, and I eagerly await our next adventure.